this is what is the general form of quadratic expression. Ax square plus bx plus c, where a, b, c are constants, and x is a variable, or literal x is a variable. So what we do first of all is that, like, we try to actually find the roots of this actually. And when we say the root of it, as in, like, if you have got expression like px, ax square plus bx plus c, and when you got p alpha equals to 0, then you say that alpha is a root or a 0 of x square plus bx plus c, or px. So alpha is the root, or you can as well say that x minus alpha is a factor of ax square plus bx plus c. This is what is the factor theorem as well, which I don't know whether we learned or not. So x minus alpha is gonna be a factor. So in general, like, for an n degree polynomial, there are at most n roots. So we say that for an n degree polynomial, which is like this, a0 plus a1x plus nx to the power n. So the theorem says that for an n degree polynomial, there are at most n roots. So there are at most n roots, meaning that, I mean, it could be less than that, but it cannot be more than that. It will be at maximum, it will be n. So using this quadratic expression will have at most two roots. Okay. So this px, or rather say that this ax square plus bx plus c equals to 0, will have at most two roots. So what we mean by two roots, meaning that the values of x for which this expression will turn to 0 is what is that we are saying. So when we are saying at most two roots, it of course means that either it could have 0, or it could have one root, or it could have two roots. This is what we'll be having, and we'll be looking at as to what does it mean to have one root or 0 root or two roots, right? First of all, like, how do we find the roots of this is, like, there are multiple ways. So methods to find, so we say that methods to find, I don't know whether that's been taught to you already. The methods to find the roots of x square plus bx plus c is, like, we have what we call as the factorization method, first of all. Splitting, or you can say this middle term splitting as well. And then we have got what we call as the completing the square method. And finally, what we have called is what we call the expression, or we have. And the formula is generally given by x is actually equal to minus b plus minus b square minus 4ac upon 2a. And when you look at this, basically this b square minus 4ac is what we call as t, or discriminant as well. This name is given to this is discriminant. And basis discriminant, there will be, you can decide whether there are gonna be one root, two roots, or actually 0 roots. So this expression, like when d is actually less than 0, when you evaluate d to be less than 0, then we say that no real roots. So later on, we will learn that there will be some imaginary roots existing, and they will be existing in pair. So I would write it here because I don't know whether they will be already written. So no real roots. You can say that imaginary roots, and the imaginary roots, they will occur in pair. They will occur in pair. So what we mean here is that, say, if your one of the root is alpha plus I beta, wherein I is iota symbol is used for the imaginary number, to square root of -1. This is what is I for. So then the other root will be alpha minus I beta. So they will be occurring in this sort of pair if they have d is less than 0. When your d is actually equal to 0, then we say that the real and equal roots. We say that real and equal roots. So these roots will be real and equal, and actually there will be one root. That's what it will be. Or you can say that, or you can say that one root in this case. And then when d is greater than 0, then again it will be, there will be real roots, and then of course there will be non-equal roots as well. So there will be certain more varieties to it. They will be writing this. If d is a perfect square, for example, if d is a perfect square, then fine, right? So d is a perfect square, and then when d is not a perfect square, so there will be two situations. D is not a perfect square. So when d is not a perfect square, what you will be having is that two irrational roots you will be having. And d is a perfect square, then you will have rational roots, of course. There's two irrational roots as well will be occurring in pair, basically. So again, if one expression is alpha plus root beta, I shouldn't be writing alpha alpha, otherwise it will be confusing. I should be writing a plus ib, so that because alpha and beta is actually we use it for the roots. So if this is alpha a plus ib, this will be a minus ib. Similarly, if I'm using a plus root b, one of the roots is, then the other root will be a minus root b. Okay. So sometimes they will just give you one of the roots, and then you got to assume the next root would be this. Okay. So nature of the roots is what we discussed. So if this is greater than discriminant is greater, then roots are equal and distinct. Sorry, real and distinct. So they are distinct roots, two roots. Here, if they are equal, then roots are real and equal. If less than 0, then roots are non-real complex and conjugate to each other. This is what is, they will be conjugate to each other, and they will occur in pair. In then this is then they are talking about the cases wherein these are rational numbers. They are saying here real numbers. It could be any number. It could be even your what you call irrational as well. Here it has to be rational, and this is a kind of expression like they are looking at. So so this is what we talked about. Like if delta is greater than 0 and it's a perfect square, then the roots are rational and distinct. If delta is greater than 0 and not a perfect square, then root are irrational and conjugate to each other is what we were talking about. If equal to 0, then roots are rational and equal, and then it is non-real and complex to conjugate to each other. So same thing, same stuff. Only thing is that um, the expression here ABC has to be basically rational number for this to happen. Okay.